Then we have plus a fresh parameter which is called lambda, then multiplied by the function we have over there, which is in terms of x1 and x2. So this simply implies that we have phi of x1 comma x2 is equals to the utility function given to us from the question, and that is what? A ln x1 plus 1 minus a ln of x2, then plus lambda of whatever I have here, which is lambda p1 of x1, then plus lambda, we multiply this p2 of x2, and minus what? Lambda of what? Lambda m. So then after this, all we have to do now is to differentiate um, the phi function partially with respect to x1, and at the same time differentiate um, this phi function with respect to x2, and then finally we need to also differentiate um, the phi function partially with respect to what? Lambda itself. But mind you, after differentiating it partially, you have to set it to be equal to 0. So now on differentiating this phi function partially with respect to x1, this is saying you have a is a constant. If I differentiate ln of any function, this a is a constant times, by the time you differentiate ln x, suppose you want to differentiate ln of x square. So the pattern is differentiate this x square, that will give you 2x, divided by repeat this x square back. So this gives you the final answer. Where this we cancel this, you have 2 over x. So the same thing similarly here. I have to differentiate x1. On differentiating x1, that means I have 1, okay, over what? Repeat x1 back. So just with what I've actually done over there. So I have a over x1. Is there still, if I differentiate this term partially with respect to x1, I will have 0 because there's no x1 to differentiate. Everything here becomes 0. So then the next thing I have here, I can see x1 here. So I can differentiate this thing partially with respect to x1. And that is, I have x1, lambda is constant, p1 is constant. So if you differentiate a constant with x, the result gives you the constant back. But there's an invisible one here. 1 multiply this one, you have lambda of p1, then x1 is power of 1 minus 1. And that's x is 1 is power of 0. That gives you 1. So there is no other m to differentiate in this case. There is no other x1 to differentiate here. This becomes 0, this becomes 0. This is a constant, this is 0. So the same thing applicable for the partial derivative of the phi function given to us with respect to x2, and that will give us x2 is not here, that gives us 0. X2 is there, I'll end up having 1 minus a. If I differentiate ln x2, that will give me 1 over x2, right? So 1 over x2 plus, I have this becomes 0 since there's no x2 to differentiate, this becomes 0. And then if I differentiate this one partially with respect to x2, I'll have lambda p2, okay. Then mind you, I actually said you are equating this to be equals to 0. You must equate this to be equals to what? To 0. So finally we have to differentiate this also. On differentiating this, we have partial with respect to lambda. Lambda is not here, 0. Lambda is not here, 0. Partially with respect to lambda, I have p1 x1. At the same time, partially with respect to lambda, I have plus p2 x2. Then partially with respect to lambda, in this case I have minus m. Mind you, you are setting this to be equals to 0. So these are the terms we have. So we have a over x1 plus lambda p1 equals to 0. At the same time, we have 1 minus a 1 over x2 plus lambda p2 equals to 0. So from here, we can decide to make lambda the subject of the formula, and then we make lambda the subject of the formula in this case. So then we can now equate. So from here, we have so from this first one we have here, from a over x1 plus lambda p1 equals to 0. Let's call that equation 1. So we also have 1 minus a over x2 plus lambda p2 equals to 0. That is equation 2. And at the same time, we have this last one here, which is p1 x1 plus p2 x2 minus m equals to 0. So this is what we have. This is equation 3. So from here, let's make lambda the solution formula from here, or we can decide to solve out for x1 and x2. But since everything are all in terms of letters, I can't easily get this. So let me just go ahead and solve. So here in this case, from equation 1, we have lambda p1 to be equals to, then this a of x1 goes to the other side, that's negative of a over x1, and then by the time we multiply both sides by p1, 1 over p1, multiply both sides by 1 over p1 by 1 over p1, hence we have lambda to be equals to negative a over x1 p1. So this is the first result we have. Similarly, from equation 2, if we decide to make lambda the solution of the formula, we have lambda p2 equals to, when this goes to the other side, we have 1 minus a over x2, negative of 1 minus a. So if I multiply both sides by 1 over p2 by 1 over p2, this cancels this. I will end up having lambda to be equals to what? Negative of what? 1 minus a all over x2 p2. So this is what I'm going to have. So since lambda is equals to this result and lambda is equals to this result, then I can easily say that this is equals to this. So that means I have minus a over x1 p1 is equals to minus 1 minus a over x2 p2. Trivially, this will cancel this, right? So since they are both equal, I have x1 p1, I have x2 p2, and at the same time I have p1 x1 p2 x2. So trivially, if I want to find x1, I'll just express x2 in x2 p2 in terms of x1. So let's make x2 p2 the solution to the formula. So you can easily do that by saying multiply both sides by x2 p2. Okay, so just cross multiply. This minus and cancel minus, I have a times this, I have a of x2 p2 equals to 1 minus a times x1 p1, right? So when I divide both sides by a, I'll end up having x2 p2 to be equals to 1 minus a of x1 p1 over a. So since we have this now, we can easily input the expression I have here as x2 p2 in this third equation. So from the third one we have over there, we call from equation 3. From equation 3, we have p1, as you can see, p1 x1, see it up there, plus p2 x2 minus m is equals to 0, where p2 x2 is equals to this expression. So I'll end up having p1 x1 plus p2 x2 is what I have in this equation I have here. So I'll end up having 1 minus a of x1 p1 over a minus m is equals to 0. So from here, you can decide to multiply all through by a. When I multiply all through by a, I will have a p1 x1 plus, multiply this term by a, I will end up having 1 minus a of x1 p1 minus a times m is am equals to 0. So similarly, you can try to break this down. Yes, you can try to break this down. We have a p1 x1 plus 1 times x1 p1, that's p1 x1, minus a times this, I have minus a p1 x1 minus am is equals to 0. So trivially, this will cancel this, right? AP1x1 we cancel minus AP1x1. So whatever I have left now is I have P1x1 minus AM equals to 0. This is capital letter M, I'm sorry for that. So this minus AM moves to the other side. So whatever I have left now should be P1x1 is equals to, when this goes to the other side, I have positive AM, right? So if I divide both sides by P1, this cancel this. Hence, the demand function, the first demand function, which is x1, is equals to A of capital M over what? M1. So this is what I have over P1 rather, over P1. So this is the first result. So we are going to do the same thing similarly with what I've actually done here. Um, from this equation I have here, from this equation I have here, from x2 p2, okay, equals 1 minus a of x1 p1 over a. So, or you pick it directly from this case here. So let me asterisk this. Let's pick it from star, from equation star. Equation star says that we have a equals to 1 minus a. This is x1 p1 and this is x2 p2. So all I'll just have to do is for me to get x2, I have to make x1 in terms of x2. So let's make x1 p1 the square root of the formula by cross multiplying. So when I cross multiply, I have a of x2 p2 equals to 1 minus a of x1 p1. So this I'm looking for x1 p1, I'll divide both sides by 1 minus a, by 1 minus a. So this will cancel this. Hence, x1 p1 is equals to a open bracket x2 p2 over 1 minus a, right? So I'll multiply both sides by 1 over p1 so that this can easily cancel by 1 over p1. So this will cancel this. Whatever I have left now should be x1 equals to a of x2 p2 all over p1 of 1 minus a.